Okay, today let's discuss section 5.2, properties of rational functions. Okay, so we already discussed the polynomial functions. What is a rational function? Rational function is a ratio of two polynomial functions. So first, let's write down the definition. A rational function is a function of the form r of x is equal to p of x over q of x, where p and q are polynomial functions. And q is not a zero function. It is not a zero function. Okay, so rational function is like the rational number. What is a rational number? Rational number is a ratio of two integers, 2 over 3, 5 over 10, 11 over 12. And the rational function is a ratio of two polynomial functions. Okay, and here, of course, in the denominator part, the rational number cannot have a zero denominator. Rational function cannot have a zero function as a denominator. And for the function, the domain of R of a rational function is a set of all real numbers except those for which q is 0. Okay, so what is the domain? The domain is a set of all real numbers that make the denominator q non-zero. Okay, so that's the domain. Okay, now let's see the example. Okay, well, we list several rational functions and we try to determine their domains. Find the domain of a rational function. Okay, A, the 2x squared minus 4 over x plus 5, r of x. Okay, let's call it r of x. What is the domain? Domain is a set of all real numbers except the number for which the q is 0. So we have to study the solution of this equation. You let denominator q equal to 0. You find the solution. Okay, so this is a number we have to exclude. So the domain of R is the set of all real numbers except -5. Except -5. Okay, so how did we do? We first set the denominator equal to 0, find the solutions, and we say all the real numbers except those solutions. Okay. Second, we do the similar thing. So we set the denominator equal to 0. So here, x will be 2 or negative 2, plus or minus 2. And then we say the domain of R is the set of all real numbers except 2 and minus 2. Except here we can write it this way, plus minus 2. You can write 2 and negative 2, or you can write this way, plus minus. This is a standard notation in calculus, in mathematics. So the set of all real numbers except plus minus 2. Okay. Let's see more example. Okay. The rational function is x cubed over x squared plus 1. So we set the denominator equal to 0. If we move 1 to the other side, we will see x squared is equal to negative 1. No solution. X squared is never equal to negative 1 for the real numbers. So you don't have to accept or exclude anything. So the domain of the rational function R is the set of all real numbers, period. That's it. Punto final. Okay? And last one. We have this rational function, x squared minus 1 over x minus 1. We want to find the domain. Then you set the denominator equal to 0. You find x equal to 1. So the domain of R is the set of all real numbers except 1. Okay? So whenever you want to determine the domain of a rational function, you just set the denominator equal to 0. If you can find the solution, you will always say the set of all real numbers except those solutions. If there's no solution, you just don't write except part. You just say the set of all real numbers. Okay. And let's study this last example a little bit. X squared minus 1 over x minus 1. We know how to factor x squared minus 1. Check here. If we have a squared minus b squared, it is a minus b and a plus b. This is an important formula. You factor the difference of squares. A squared minus b squared is a minus b times a plus b. So here you have x squared. 1 is 1 squared. So the numerator can be written as or can be factored as x minus 1 times x plus 1. And then over x minus 1. Okay, so if you put parentheses here, you can see that this is a common factor from numerator and the denominator. You cancel this common factor, you get x plus 1. Right? And even though after cancellation these two functions are equal, but these two functions are different. So R of x, this rational function, has domain all the real numbers except 1. This is a rational function. The right-hand side function f of x, x plus 1, the domain is all real numbers. So when we try to say two functions are equal, not only they share the same formula, or they have the equal formula, but also they have the same domain. Okay, so here they accept the domain has except part. This domain has no except part. Since they have different domain, these two functions are different. You have two different functions. They just have a lot of same value on a lot of point, but they are different. Okay. Okay. So one thing we want to emphasize. And if for a rational function px over qx, a rational function, whenever we say if it is a rational function, we mean p, q are polynomial functions. And if p and q have no common factor, it's not like this. This one, they have the common factor x minus 1. If they do not have a common factor, then R is said to be in lowest term. Lowest terms. It's a concept. Lowest terms just means you cannot do more cancellation from top and the bottom. Okay? And if, okay, so we have the lowest term. This one is not in the lowest term. It's not in the lowest term. And if R of x is P of x over Q of x is in the lowest term, lowest terms. If R of x is P of x over Q of x is already in the lowest terms, the real zeros if you have of the numerator in the domain of R are the x-intercept of the graph of R. So what does this long sentence say? It says, for example, if you have this, rational function, you find the zero of the numerator, x is equal to 1, it is the zero of the numerator, then this 1 is also the x-intercept of the graph R. So when you sketch the graph of R, you will see the x-intercept x equal to 1. Okay? So from here, let's see, if we have R is 1 over x, for example, R is 1 over x, then the numerator is never equal to 0, or the numerator has no 0. the numerator has no 0, then the graph of R has no x-intercept. Okay, so the numerator has no 0, then the graph of R has no x-intercept. So you can just observe the numerator to determine the x-intercept. And you can do that only under the condition R is in the lowest term. If R is not in the lowest term, you cannot do it. Okay? And okay, this is a 0 of the numerator, and the 0, the real 0 of the denominator the real zeros of the denominator are not in the domain. Again, we're talking about the rational function in the lowest term, right? We always exclude the 0 of the denominator. But even though they are not in the domain, you will see that we will use it, but they are important in the graph of R. Even though they're not in the domain, but they're still very important in the graph. Okay, so that's the lowest term and the 0 numerator and the denominator. These two concepts, again, I want to emphasize. The x-intercept not in the domain, they are under the lowest term condition. Let's try to sketch the graph of a special function 1 equal to x squared. We know that x squared, for whatever x, is always positive. So 1 over positive number is still positive. So it's always above, the graph is above x-axis. So we don't need the lower part. And also the numerator is not 0 for whatever x. So there's no x-intercept. Okay? So like this, no x-intercept. And it is an even function, right? You have square. You put negative x. Negative sign will be cancelled by the square, so it's an even function. So always positive, not intersect x-axis, and even function. And then we can just choose the value. You choose x is, in the book, they provide some value. X is 1/2, x is 1 over 100, x is 1 over 10,000, and x is 1, x is 2, and x is 100, and x is 10,000. So whatever, you just use a calculator, because you have calculator, you can estimate. With them, you will see that more or less the graph is like this. It's even, so the left part is this way. So this is the graph of 1 equal to x squared. Okay, so remember we say always positive, not intersect axis. Positive, no x-intercept, and even. Even. So those three properties. So we sketch this part and reflect it about y-axis, you'll get the other part. Okay, so this is a graph of 1 over x squared. And use this graph, we can do the transformation to get other graphs. For example, let's see this. We try to graph r of x is 1 over x minus 2 squared and plus 1. So to graph this rational function, we need two steps. Step 1, we can see here, step 1. We need two transformation, 3 steps. Step 1, we sketch the graph y equal to 1 over x squared. We know what it is. It's like this. And step 2, x minus 2, we are going to shift this graph to the right 2 unit. Minus 2. You shift the graph to the right 2 unit. It's equivalent, you shift this y to the left 2 unit. So that's because I can easily shift the axis. I don't want to shift the graph. The graph I can copy. And step 3. Add 1, it means you are going to shift this the graph up 1 unit. You shift the graph up 1 unit, it means you shift this axis down 1 unit. It's just a relative motion. So I'm going to again copy this graph here. It was here, and then you shift it 1 unit down. Okay, so this is a 0, this is a 2, this is 2, and up 1 unit, this is a 1. Okay, so that's how the graph and the transformation. And in this part, we are going to study the importance of the 0 of the denominator. In order to make that precise, we need a concept called asymptotes. Asymptotes. So what is asymptotes? And check this graph. If you check it, my graph is horrible, but if you check it, if I get it a bit better, let me do it here. Okay, there's no intersection, just close and close. If we check this graph, we will see that when x becomes bigger and bigger and bigger, like when x approaches past infinity, when you follow the curve, you will see that this curve is almost this horizontal line. And similar thing, if you let x approaches negative infinity, move to the left, this curve will be almost the horizontal line. So this is a horizontal situation. In a vertical situation, you will see that when x approaches 2 from right and from left, the graph, of course, it's a curve, but it's very, very, very close to a straight line. We like straight line. Curve is curved, so it's not easy as a straight line. Okay, so in order to describe this kind of a phenomenon, we get the asymptote. So definition, like approximation. Let R be denote a function. This is not just for rational function, it's a general concept. Let R denote a function, not necessarily rational function. if as x here approaches negative infinity, or as x approaches positive infinity, it means it is either very, very negatively large or very, very positive large, or, not all, both, just one. The value of r of x approach some fixed number, some fixed number L, then the line y equal to L is a horizontal asymptote. Is a horizontal asymptote. Okay, so here this is like the one of example, but usually the general example is like this. So your graph, possibly you see here, you have a whatever shape, but eventually it approaches. From the graph, you will see that when x approaches positive infinity, the graph is very, very close to L. If this happens, this L, y equal to L, this line, horizontal line, y equal to stuff, that y equal to L is a horizontal asymptote. It can approach L from this direction. It can also approach L from this direction. Okay, this is also approach L. Or it can also approach L like this. So it's not always above or below. It's kind of like a wave, but closer and closer, narrower and narrower, and eventually to the L. So either way. So all three cases means this horizontal line y equal to L is a horizontal asymptote. If it is a horizontal asymptote. Okay? So it can be always above, always below, but it can also be like up and down infinitely many times. Okay, so this is a horizontal version. What is a vertical version? If as x approaches some number c, the value, absolute value of r of x approaches infinity. Okay, then the line x equal to c is a vertical asymptote of the graph. Of R. Okay, so what does this mean? This means, you see here, when this x approaches point C, this is point C. X equal to C is a vertical, y equal to L is a horizontal. And the absolute value of r of x, the value approaches infinity. It can be like this. It can also be like this. Because absolute value, when we put absolute value, this it becomes positive, but still approaching infinity. It just go down, down, down. Or it can be like this. One direction is positive, the other direction is negative. So either works. Whenever you see the graph is one of them, this vertical line x equal to c is called a vertical asymptote for the graph of R. Okay, it's not always positive or always negative. It could be one is positive, one is negative. Okay, that's allowed. So this is a definition of an asymptote. It describes the so-called the end behavior. Remember that the end behavior at infinity. What is the behavior? At infinity, asymptote just means the graph is like the straight line. At infinity, the graph is like the straight line. That's what the asymptote wants to describe. Okay? And there's a small difference between the vertical asymptote and the horizontal asymptote. You see here, for the vertical asymptote, for the horizontal asymptote, we have the case 3. The case 3, this is a horizontal asymptote. The graph intersect the horizontal asymptote infinitely many times. You can have intersection. But if you talk about the graph, so let's say this. 1. The graph of a function may intersect a horizontal asymptote. Sorry. ASYMPTOT. Yeah. It may intersect horizontal asymptote. Like this. But if we back to our rational function and the vertical asymptote, the graph of a rational function. The reason we put a rational function is that we need a continuity. The graph of a rational function will never intersect a vertical asymptote. So vertical asymptote is something you will not touch. The horizontal asymptote, you can still touch it. Okay, so this is a vertical, the small difference between vertical and horizontal. You see here, when you have this, you will never make the intersection between the vertical asymptote and the graph of the curve. And this place, we emphasize, for the vertical asymptote, we only consider rational functions. We don't expand our class of functions. Okay, so horizontal, vertical, and sometimes this line is not that special. If it is not horizontal, not vertical, it's called oblique asymptote. It looks like this. If when x approaches infinity, the graph of the function is close to this line with a non-zero slope, then this line is called a vertical asymptote. So we make the definition. If as x approaches negative infinity or x approaches positive infinity, the values of R of x approach a linear expression ax plus b. Here a is not equal to 0. If a is equal to 0, it becomes a straight number that is horizontal. If this happens, ax plus b, then the line y equal to ax plus b is an oblique asymptote. Okay, so that's an oblique. Oblique asymptote just means it's not horizontal, not vertical, but still it is a straight line and the value of this function approaches it. And because it's not vertical, only vertical asymptote cannot be touched. Because it's not vertical, the graph of a function may intersect an oblique asymptote. So oblique asymptote can be touched. You see here, horizontal asymptote, slope is 0. Oblique asymptote, slope is a. So whenever you have slope, that asymptote can be touched. Vertical asymptote has no slope. You cannot touch it. Okay, that's a way to memorize it. Whenever this asymptote has slope, it is possible to intersect. When the asymptote has no slope, vertical one, you cannot touch that vertical asymptote. Okay. Now let's just focus to the rational function. We try to find a vertical asymptote. So here it's a general discussion, not the vertical asymptote of a rational function. The vertical asymptote of a rational function, let's check. Assume this rational function is in its lowest form. In the lowest form. And R is a 0 of Q of x. R is a 0 of the denominator. Remember that this R is not in the domain. R is not in the domain. R is the 0 of the denominator. So R is not in the domain. It's in the except part. Okay, so since this is lowest term, not form, sorry, lowest terms. This part, lowest terms. The concept is lowest terms. Since this R is already in its lowest terms, P and Q have no common factor. Px, Qx have no common factor. So P and Q have no common 0. They have no common factor, then it means those two polynomials have no common 0. It also means R is a 0 of Q. R is not a 0 of P. It is a 0 of one polynomial. It will not be a 0 of another polynomial. It's not 0 of P, so P of R is not equal to 0. Now let's check. When we see the behavior near 0. When x is close to R, when x is close to R, then Px is close to P of R. not equal to 0. But this function, rational function, r of x is going to be p of x over q of x. It's about p of r over q of x. But q of x approaches 0. Q of r is 0. Q of r is 0. So a number over 0 will give you a large term. So this one approaches infinity or negative infinity. It depends on the sign. So that's the reason we put ops value. When we put ops value, we will kill this plus minus sign. It's always positive infinity. Okay? So because of this, we see that whenever you have the 0 of the denominator comes from the lowest terms, then x close to r, the behavior near this 0 will be infinity. So that gives us theorem. A rational function r of x is equal to px over qx in lowest terms will have a vertical asymptote x equal to r if and only if r is a real 0 of q of x, of the denominator. Okay, so whenever you have the 0 of the denominator, you will have a vertical asymptote. Under the hypothesis, it is already in its lowest terms. Okay, so let's see the example. Because the numerator, in this case, numerator is not 0. Denominator becomes smaller, approaches 0. So you divide a number by a very small number, you get a large value. Okay. So the rational function x plus 3 over x minus 1. And we just, first, they don't have a common factor, so the function is in lowest terms. And second, the denominator has 0, 1. The denominator has only one solution, x equal to 1. So the vertical asymptote is x equal to 1. X equal to 1. Okay? So lowest, the vertical asymptote is x equal to 1. This is the first example. Second, you get x over x squared minus 4, and this is in the lowest term. So to find the vertical asymptote, you solve x squared minus 4 equal to 0. You will get x is 2 or x equal to negative 2. Two solutions. And then you will say the vertical asymptote are x equal to 2 and x equal to negative 2. So here is a funny thing. At this place, 2, negative 2 represent numbers. So x equal to 2, x equal to negative 2, they represent numbers. But whenever you talk about the vertical asymptote, you also write x equal to 2, x equal to negative 2. These two things represent lines. So this is a vertical line. these two vertical lines. So that's a, you see here you have the identical expression, but when you write this expression in the solution of equation, they are numbers. When you write a representation in the vertical asymptote, they are vertical lines. Just be careful. Just be careful. Okay. Next. H of x is x squared over x squared plus 1. And first, this is in the lowest terms because the numerator and denominator have no common factor. We say they don't have common factor. Even though they share the same x squared, they are not factor, they are terms. Right? Be careful. This is not the common factor. They are just the same term. You cannot cancel them. You can never cancel them. Okay, so it is in the lowest term. Let's solve the equation denominator equal to 0. X squared plus 1 is 0. X squared is negative 1. No solution. Again, this denominator equal to 0 has no solution. Then we say there's no vertical asymptote. Asymptote. There's no vertical asymptote. Okay. So once you solve for the denominator equal to 0, you don't find any real solution, then you say this rational function has no vertical asymptote. Last example. You have this rational function, x squared minus 9, x squared over x squared plus 4x minus 21. Whenever you want to apply the theorem, find the 0 of the denominator and get the vertical asymptote, you have to first examine if it is in lowest terms. So we need to factor. X squared minus 9 is x squared minus 3 squared. Again, let me copy it here. X squared minus 3 squared. Remember that a squared minus b squared is a minus b times a plus b. Okay? And the denominator, 21, negative 21 is 7 times negative 3. Okay? So after factorization, you see here, they do have the common factor. So you have to cancel this common factor. Then you get the lowest terms. So this is the lowest terms. To apply the theorem, you must study this expression, not the original expression. In this expression, you set the denominator equal to 0. You get x equal to negative 7. So the vertical asymptote is only x equal to negative 7. This is a unique vertical asymptote. Okay? So we know how to find the vertical asymptote. Under the hypothesis, the rational function is in lowest term. Okay, and now let's try to study the horizontal asymptote. First, the rational function has two polynomials, p and q. Possibly, the degree of the numerator is less than the degree of the denominator. Possibly. So, if the degree of the numerator is strictly not equal, not without equal case. If the degree of the numerator is less than the degree of the denominator, if this happens, R is called proper. R is called proper. So for example, R of x is 1 over x, or R of x is x squared, 1 plus x cubed, so they are proper. Okay? And of course, if you have R of x equal to x squared plus 1, x squared plus 2, or R of x is x cubed plus 1, x squared plus 1, something like this, then they are improper. They're not proper, improper, whatever. So first we study this case, the proper case. Okay, so we study the case when the degree of the numerator is less than the degree of the denominator. And in this case, we have a theorem. We say if a rational function is proper, then the line y equal to 0 is a horizontal asymptote. TOT, yeah, it's a horizontal asymptote. Actually, it is a unique horizontal asymptote. Why do we have this theorem? So remember, when we sketch the graph, we have that under behavior. Under behavior of a polynomial means when x is very large, negative or positive infinity, the polynomial is almost the first term. The polynomial is almost the first term. So assume this p of x, px is a an x to n, an minus 1 x to n minus 1 stuff, and q of x is bm x to n to m bm plus 1 So at infinity, this tail, you can ignore them. So you only consider the leading term, an x to n, bm x to m. If it's a proper means n is less than m. So the rational function p over q is about an x to n, bm x to m. N is less than m, so it's about 1 over x m minus n. So basically, you only with the coefficient an over bm. Basically, you only need to study the function 1 over x to nth power. Here's positive. X to some case power. Let's use capital F, not R. X 1 over x to k's power. If k is even, it's like this. If k is odd, it's like this. But either way, you will see the horizontal asymptote is x equal to 0. Y equal to 0, sorry. Y equal to 0. So that's a reason we say one horizontal asymptote, actually the unique one. Okay? So that's a reason. This is the under behavior. This is under behavior. So the example will be very simple because we only study the proper rational function. So if we have r equal to like x minus 12, 4x squared plus x plus 1. This is proper. It is proper. You just check the degree. Degree of the numerator is 1. Degree of the denominator is 2. So it's proper. When it is proper, then y equal to 0 is the unique horizontal asymptote. Okay, so you just pick up whatever proper function, you will always get y equal to 0 as a horizontal asymptote. Okay, we stop here and we will continue the discussion oblique asymptote for the improper rational function in the next part. Okay.